All right.
Next. So we're going to choose W1 such that A times W1, so A times W1 is not 0. We don't want W1 to die right away on the first application. But A squared of W1 is 0. Okay? So what I'm going to do here is just tell you what A squared is. I've been doing that all along in lecture and class as well, because I'm assuming you guys can square these matrices out. You just have to take the original A and multiply it by itself. Just be careful when you're doing it so that you get it right. So I'm going to tell you what it comes out to. 0, negative 9, 0, 0, 1, 0, and 0, negative 2, 0. That's what I ended up getting. Okay, so can somebody give me a vector, W1, that will survive this matrix, but will not survive this matrix?
1, 0, 0. Oh,
Okay, there's actually lots of right answers. I'm going to choose the easiest thing I can absolutely try. I'm going to try 1, 0, 0. We'll see if it works. So 1, 0, 0. When I multiply it by this matrix, okay, one thing I want you guys to be kind of starting to learn here is that when you multiply it by the original matrix, what happens is you strip off the first column of the matrix. In other words, so if I take the original matrix, negative 2, negative 1, 4, 0, negative 1, 0, and negative 1, negative 3, 2. If I multiply that by 1, 0, 0, it just gives me the first column. This is my point.
Okay.
So this is W1 right here, and this is W2. Now, is it fair to say that W1 will die if I apply A squared to it? Yeah, because if I put 1, 0, 0 next to this matrix, it again strips off the first column, but the first column is all zeros. Okay, so that does work. Okay, so that is a good, perfectly good solution. So I need to write down what x2 is now. x2 is, well, e to the 0 again, times W1, which we have chosen as 1, 0, 0, plus t times W2, which was negative 2, 0, and negative 1. Okay? This W2 vector is always going to be an eigenvector. Well, if you look back to the eigenvector that we found originally over here, 2, 0, 1 that we found, sure enough, this is just a multiple of that eigenvector. Okay, so we're kind of 2/3 done. Would you guys like me to derive the other, the third solution, or are you willing to just have me write it down for you?
Yeah, just write it down.
Can I just write it down? Maybe to save the time, because this is like getting to be the computational stuff. Let me just write down the last solution right here, and then I think you guys are pretty much going to be on top of it. So my other eigenvalue is negative 1. And you just have to find the eigenvector for that. It turns out, I'm going to let you guys check this just so we save a little time. 9, negative 1, and 2 is the vector that you're going to come up with for that. And so your x3, your third solution, is e to the negative t times 9, negative 1, 2. Okay? Let me just do a quick follow-up on this. So I found, well, I guess I'm not done, am I? I found the 3 individual solutions, but then...
You need to find the initial.
Okay, before I go any further with the problem, I'm going to just go a quick diversion here. If I asked you to write down the fundamental matrix for this linear system, would you know how to do that?
You have the columns, the vectors as the columns of the matrix.
Right, so this was in the group work that we had this week, and a lot of people had forgotten what this was, so I just want to remind you again. Essentially, you just take the 3 solutions that we have. So here's one of them here, here's the second one, and then the first one is just this right here, vector 2, 0, 1. You just simply take those 3 solutions and you slam them into the columns of a matrix. So here's the first solution that we had earlier.
Yeah.
And then the second solution, I'm just going to go ahead and compress it into a single vector. So 1 minus 2t, and then 0 and then negative t. Does everybody see what I just did?
Yeah.
I just took this thing and compressed it into that column. And then the last solution is going to be 9e to the negative t, negative e to the negative t, and 2e to the negative t. So it's basically going to be that 3 by 3. If I ask you for the fundamental matrix, that would be it. It turns out, in the very, very last section of the course that we have not quite covered yet, we're going to need the fundamental matrix again. So there is a reason that I keep asking for it. It is going to make another appearance before we're all said and done. But I'll tell you about that next week. In the meantime, I can go ahead now and write down my general solution. So C1 times 201 plus C2 times the second solution, which I guess I'll just put it from right here, 1 minus 2t, 0, and negative t. And then the third solution, 9e to the negative t, negative e to the negative t, and 2e to the negative t. That's the third solution. Okay? Everybody following me? You see the difference between the fundamental matrix and the general solution? They're very similar. The general solution has the constants in front. You're just adding the terms. Okay? Now, there was an initial condition given. I'll just write it down again here for those of you watching from home so you can see it right on this board. Negative 2, 1, and 1. That was the x of 0. So if I put in 0 for t here, let's just see what happens. We're going to get C1 times 201. I'm putting in 0 for t everywhere, so 1, 0, 0 times C2. And then the third one, when I put in 0 for t, of course, e to the 0 is just 1. So I'm just going to get 9, negative 1, and 2. All of that has to equal negative 2, 1, and 1. Okay? This is actually giving you 3 equations and 3 unknowns, which you could set up as a system and then work on solving it. I'm going to do it quickly here because it's actually not too bad. If you read across the middle row, there's no C1s, there's no C2s. Negative C3
is equal to 1.
So C3 is
negative 1,
right? Okay. Now, if I take that information and use it on the bottom row next, C1 plus 2 times C3 has to add up to 1. So what's C1 going to equal?
3.
C1 plus 2C3 equals negative 1, right? So C3 is negative 1. No, this is equal to 1, sorry. Okay, C1 plus 2C3, I'm reading on the bottom row, adds up to 1. So if I put in negative 1 for C3, then this is negative 2. Add it to the other side, you should get 3.
Yeah.
Okay, great. And now, from the top row of this little system here, 2 times C1, which is 6, plus C2, plus 9 times C3. So 6 plus C2 plus 9 times C3, that'd be minus 9, adds up to negative 2. So we should get C2 equal to
1.
1. Right. Okay, so now I have my constants, and then you could go back and feed those in here. 3 goes here, 1 goes here, and negative 1 goes here. That's the way that's going to work. Okay. Everybody feel pretty good with that?
Yeah.
Okay, great. So I've reviewed, of course, in doing these 2 problems, we've reviewed an immense amount of stuff. We've reviewed, first of all, 7.4 with complex numbers in it, 7.5 with the W's in it. Now, there's other cases, of course. There's the case where you have the W3, W4, W5, stuff like that, right? This review, again, I've said this at review sessions before, you're not going to walk out of here tonight necessarily having seen absolutely everything totally in thorough detail again. You're seeing a smattering of different things to try to remind you what are the things you need to go back and review. But these 2 problems, they also have reviewed the lambda stuff, finding the eigenvectors, eigenvalues, all that good stuff, putting together a general solution. This is really good stuff. So I'm trying to make myself feel better because I've only done 2 problems. I've been here for an hour now. Okay, but that's the way this goes sometimes. All right. Why don't we change and work on something a little different? So I'm going to jump around. I've done problems 3 and 4. Problem 1 I did in class, and problem 5 is actually from a group work that you guys already have looked at, so I'm not going to do those. I think what I'll do maybe one more computational thing for now, and then we'll maybe do a few theoretical problems, because everybody wants to see the theory problems. The theory problems, just like the other midterms, will probably be 15%, maybe 20% of the grade. I will probably try and set it up where you'll have a choice, so you don't have to get everything right on those, or I'll drop a problem or something, but there might be multiple things to choose from, because some people, it sort of either hits you or it doesn't, and I don't want to sort of put that pressure on you that you have to see everything, but we do definitely want to practice that stuff. Okay, so but before I do that, let me just do one more example. This is going to be part 6C on the review sheet. I want to solve y double prime minus 8y prime plus 17y equals e to the 4x times the cosecant of x. Half the battle is just figuring out like what type of problem is this, and get our heads into the correct chapter of the book for this, and then the correct method that you need. So anybody brave enough to tell me what this has anything to do with?
The variation.
Right. Why, Alec, why is it variation of parameters? Outstanding. Yeah, we don't know how to annihilate cosecant, and it's a second order equation. So, I mean, some second order equations we can use annihilators for, but if we don't know how to annihilate the right hand side, then we're going to have to use the variation of parameters method. And also, just make sure you recognize this is not a vector differential equation. I'm not trying to solve for a whole column of unknowns. This is a scalar function. So I know this is chapter 6 that we're looking at right here. Okay, so if I'm going to do variation of parameters, what's my first step?
Homogeneous equation.
The corresponding homogeneous equation, which is where you just basically set everything equal to, set the whole thing equal to 0. That's the homogeneous differential equation that corresponds to the original one. And how do I solve the corresponding homogeneous equation? Right, I need the auxiliary equation. And what would be the auxiliary equation for this problem?
R squared minus 8r plus 17 is equal to 0.
Equals 0. There we go. That's the auxiliary equation. It's just a quadratic. Anything quadratic, of course, we can always solve. So the auxiliary equation, we can always solve this one by just using the quadratic formula if we need to. 17 is not a very nice round number, so chances are I'm going to need to use the quadratic formula here. So everybody has to know this one. I changed the sign of the b term, so it becomes a plus 8. Plus or minus the square root of b squared, well 8 squared would be 64, minus 4ac. So that's 4 times 17, which is 68, great. And I divide all of that by 2. Okay, so 8 divided by 2 is 4. And then, let's see, this is the square root of negative 4. Square root of negative 4 would be 2i, which is then being divided by 2. So it would just be
I.
Right. Okay, so 4 plus or minus I. Great. So then I can write down my, what we call the complementary function. This is all part of the step. Remember, there's 3 steps. So we're doing step 1 right now. So the complementary function here would just be what?
E to the 4x.
There should be a c1 in there.
Oh, yes.
Times
E to the 4x.
e to the 4x
Cosine x.
cosine x, great, plus
C2.
c2
E to the 4x sine x.
e to the 4x sine x. All right, everybody okay with that?
Yeah.
Now on the variation of parameters method, remember that we have to identify the y1 and the y2 of the solution, because we're going to need that for the next step. So I'm just going to label them that way. Remember that there is no right or wrong way to order these two terms as long as you're consistent as you do the rest of the problem. It'll be fine. So just do it the way I've done it there on the board. Okay, so that's step 1. So for step 2, can somebody remind me, what am I going to need to do on step 2 now? I need to figure out the U1 and the U2, and the formulas for both of those require us to have the
Wronskian.
So I'm going to find the Wronskian next, just so we get that taken care of. So the Wronskian, I'll just call it W, just to say writing. So the W is equal to, this is just the determinant of, now this will be a 2 by 2 matrix. Remember how this works? We put our functions on the top row, so we have e to the 4x cosine x and e to the 4x sine x on the top. And this is going to be a little bit of a pain because I have to take derivatives now, and that's going to require me to do what?
Product rule.
The product rule, exactly. So I'm going to have to use the product rule, so I'm going to take the e to the 4x times the derivative of cosine, which is negative sine. I'm sorry I'm writing this so small just to make it fit. And then plus the derivative of e to the 4x, which is 4e to the 4x, times cosine of x. Okay, I really didn't make my matrix big enough, did I? Need more room here, sorry. Okay, so we'll stretch that out a little bit. The second derivative is just going to be e to the 4x cosine of x plus 4e to the 4x sine x. Make sense so far? It's just a 2 by 2, so I just need to do my basic formula for the determinant here. Let me try and write it out. E to the 4x cosine x, that's the upper left corner, times the bottom right corner over here, so that's e to the 4x cosine x plus 4e to the 4x sine x. I'm going to have all of that right there. And then minus e to the 4x sine x times, well, it's going to be negative e to the 4x sine x plus 4e to the 4x cosine x. I sure hope something's going to cancel. Otherwise, it's not going to be very easy. Is anything canceling?
Yeah.
Okay, there's an e to the, so there's e to the 4x times e to the 4x ever. It's not really canceling, but e to the 4x times e to the 4x would become
E to the
e to the 8x, right? So I could factor that out if I wanted, e to the 8x. All right, and let's just see what we're left with. Well, right here I have cosine squared. Okay, and then on this one I have plus 4 cosine sine, 4 cosine x sine x, like that. Okay. And then what do I have on this side? Well, I have a double negative here, so it actually becomes a plus sine squared. All right, and then I have a minus, don't forget this is a minus, 4 sine cosine. Sine x cosine x. So all of that is like factored out from the e to the 8x. Anything canceling?
Yeah, the 4.
The terms that are multiplied by 4 are just